Welcome to Interview Breaker. Today we're diving into an advanced Swift topic, cases where value types can be stored on the heap and reference types on the stack. Understanding these scenarios gives us a deeper insight into how Swift manages memory and how compiler optimizations come into play. In Swift, the general rule is that value types like structs, enums, and tuples are stored on the stack, while reference types like classes are on the heap. However, there are exceptions. Let's start with value types on the heap. Value types in Swift include structures, enumerations, and tuples. By default, these are stored on the stack for efficiency. However, they can be stored on the heap under certain conditions, captured by escaping closures. When a value type is captured by an escaping closure, a closure that is called after the function it was passed to returns, it must be stored on the heap because it needs to outlive the function scope. Large value types. If a value type is large, the compiler may decide to store it on the heap to avoid stack overflow and improve performance. Copy-on-write mechanism. Swift's standard library collections like array, dictionary, and set are value types that use copy-on-write (cow) optimization. They share a single heap allocation until a mutation occurs. Indirect enumerations. Enums declared with the indirect keyword store their associated values on the heap to support recursive data structures. Stored in reference types. If a value type is a property of a reference type, class instance, it resides on the heap as part of the object's storage. Now, let's talk about reference types on the stack. Reference types in Swift primarily include classes and functions closures. They are generally stored on the heap, but there are exceptions. Compiler optimizations, escape analysis. The Swift compiler can perform escape analysis to determine if a class instance does not escape the scope and can be safely allocated on the stack. Unmanaged references using unmanaged TIA. Developers can manually handle the memory of reference types, potentially storing references on the stack. Caution: this is unsafe and bypasses ARC, so it should be used with care. Non-escaping closures. Reference types captured by non-escaping closures may be optimized to reside on the stack since they don't outlive the function scope. Without actually escaping function. The standard library function allows you to temporarily treat an escaping closure as non-escaping, enabling stack allocation of resources used within the closure, automatic reference counting, optimization. ARC may optimize away retain release calls for short-lived objects, effectively making their usage similar to stack allocation. And additional details you might want to know too: variables versus instances. The variable, reference to a class instance, is stored on the stack, but the instance itself is on the heap. When value types are part of a heap allocated object, for example as properties of a class, they reside on the heap. Stack allocation benefits: faster allocation, deallocation, and better cache performance. Heap allocation overhead requires dynamic memory management, which is slower due to allocation, deallocation, and potential fragmentation. Limitations. Complex scenarios. The compiler might not optimize stack allocation if it cannot guarantee that the object doesn't escape, such as through global variables or closures. Best practices. Trust Swift's compiler optimizations for memory management unless profiling indicates a problem. Prefer value types for simple data structures, but be mindful of their size. Be cautious with unsafe code. Manual memory management can lead to undefined behavior if not handled correctly. Conclusion: in Swift, while the general rule is that value types are stored on the stack and reference types are stored on the heap, there are exceptions influenced by language features and compiler optimizations. Understanding these exceptions is crucial for writing efficient and safe code, especially in performance-critical applications. By being aware of these scenarios, you can better predict the memory behavior of your Swift applications and optimize them accordingly. If you found this video helpful, please give it a thumbs up, share it with others, and subscribe to Interview Breaker for more in-depth Swift and iOS development content. Hit the notification bell to stay updated. See you in the next video.